Hey class, how are you doing? Here's the video for ventilatory threshold, anaerobic threshold, lactate, and fuel utilization. This is one of our labs in class, and it's a fairly interesting one, I believe. So just as a precursor to everything, anaerobic threshold, what this is typically defined as, is the point where an individual transitions between aerobic energy systems, so mostly mitochondrial based things, towards anaerobic systems, so kind of increase in exercise intensity or difficulty. So we can't make ATP aerobically anymore, so we have to start relying back on the anaerobic systems. So this is really important for overall sports performance in just about every sport. Aerobic capacity is one aspect of sports performance, like how an individual can be good at it, so to speak. And here I have aerobic capacity defined for you. So that is just the maximum amount of oxygen that can be transported and utilized by a skeletal muscle. Now, the problem with this is that the aerobic capacity, or it's frequently called VO2 max, this happens after an individual's anaerobic threshold. So what an anaerobic threshold is, I actually have this defined in a couple of different places, but here is one of them, or one of the definitions for it. So this point during exercise, which lactic acid starts to accumulate in the muscles, and we start feeling more of a burning sensation. Things start getting more difficult. People tend to respirate more frequently. This anaerobic threshold, lactate threshold, ventilatory threshold, they all essentially mean the same thing, that we can no longer meet our energy needs aerobically, and now we're shifting towards anaerobic means, so the difficulty is increasing quite a bit. And we're going to be measuring this in class today with our new metabolic cart. So that's going to be pretty awesome. We're going to be measuring a person's oxygen consumption, CO2 output, their respiratory exchange ratio, and all sorts of other things. It's going to be pretty cool. So here, go ahead and read through this a little bit. I will talk about all of this just slightly more in class, um, but I think this should get us kind of on par with it. One thing that I want to point out right now is OBLA, or the onset of blood lactate accumulation. So this we will be measuring, and I'll show you how to measure it in a video, and I'll probably be measuring it on whoever's running in class. But this is where blood lactate starts to get up to 4 millimoles per liter, and then it essentially has an exponential increase and skyrockets up. So this should be somewhat apparent in class. Generally, at rest, we have about 1 millimole of lactate, and then as we increase exercise intensities, it goes up a little bit, and then once we get near our anaerobic or lactate threshold, then it's right at around 4, and then it starts going up to 6, 7, 8, and sometimes even higher than that. So hopefully that'll make some sense. Next thing, fuel utilization and what's called the respiratory exchange ratio. So an interesting thing is we can actually tell what fuel someone is utilizing to make their ATP based upon how much CO2 is coming out of their mouth and how much O2 is going in their mouth. And this is due to like some fairly simple chemistry and just a little bit of math. If you look at this right here, the general equation for respiratory exchange ratio, or sometimes it's just called R or RQ, respiratory quotient. So here that's division, that's what quotient means, right? Dig it? All right. So if we look at this, this is the 16 carbon typical saturated fat that people would burn. So palmitic acid, C16H32, O2 plus 23 oxygens. And over here, that yields 16 CO2 and 16 waters. So if we do this math right here, if we just put CO2 over on this product side in the numerator and O2 from right there in the denominator, we get a 0.7. So if someone has a respiratory exchange ratio of around 0.7, that means they're burning almost exclusively fat for fuel. Now, conversely, if someone has a respiratory exchange ratio of 1, here glucose C6H12O6 plus 6 oxygens yields 6 CO2 and 6 waters. So CO2 divided by O2, right there, 6, that's 1. So if someone has a respiratory exchange ratio of 1, that means they're burning exclusively carbohydrate for fuel. So normally, as exercise intensity goes up, we have this crossover concept. So here, percent VO2 max, increasing exercise intensity. At lower intensities, we burn a little bit more fat, a little less carbohydrate, and as it gets a little bit more intense, we burn more carbohydrate. So that's fairly interesting. Up here, we're going to have to be doing some math with this today. So percent of fat, and here are all of our R or RER equations, not equations, RER values. So 0.7, 100% fat, 0% there, 0.75, 83, 17. So an interesting thing with this, we can figure out how many calories that someone is burning per liter of oxygen consumed. So an interesting thing here is that for the more fat versus carbohydrate, it's actually a little bit, we get more calories per liter of oxygen with carbohydrates than we do out of fats. So overall, it actually is a little bit more efficient for our cells to burn carbohydrates for fuel. That's really why we do it at higher intensities, because we need more ATP, and we don't have as much time to consume oxygen. And I think this makes sense aerobically. If we just notice right here in palmitic acid, oxygen, that's just, there's 2 of them right there, and here's 6 of them in glucose. So we actually don't need to put as much oxygen into this carbohydrate equation to get it balanced out, but we need to consume a lot of oxygen in order to oxidize or burn fat. Hopefully that makes sense. It'll make more sense as we're going on. And we will be using this chart quite a bit in class. Something else down here that we can figure out is like maximum fat oxidation. So frequently in exercise classes, it's asked, what's the best exercise to burn fat? Now, the lower the exercise intensity, we're burning a higher percentage of fat, but actually at slightly higher exercise intensities, we're burning a lower percentage of fat, but we're burning a higher total amount of fat. So that should be relatively interesting to most individuals that are interested in like body composition. So what we're going to be doing in class, there's only going to be one person who's exercising, and the protocol is actually on the Excel document. You're going to need to make 3 graphs and answer 3 questions. So these 3 graphs right here, blood lactate on the y-axis and stage on the x-axis, ventilation on the y-axis, VO2 liters per minute on the x-axis, VCO2 y-axis, VO2 on the x-axis. And hopefully we've made enough graphs to where that makes sense to you. And here are a couple of questions that should be relatively easy from taking everything down on the Excel document. What was the percent of VO2 where the subject switched from burning primarily fat to carbohydrate, the crossover point? So essentially we're just going to be looking at where their respiratory exchange ratio switched from 0.85 to a little bit higher than that. Then what percent of VO2 max did they reach their highest fat oxidation? We're going to have to do a little bit of math at that. And then here, what percent of VO2 max did they reach onset of blood lactate accumulation? So we're going to be measuring their blood lactate, and we'll see where they got to 4, essentially. So the procedures, this is what's happening. If you look at the Excel document, I gave you this document. what we're going to need is one person to volunteer to run in class today. So we could either run. So here's the protocol for running. So essentially what it is, we're going to take some values at rest. And then the first stage is going to be walk in 3 miles per hour at a 2% grade, then run 6 miles per hour, 2% grade, 6 miles per hour, 4%, 6%, 8%, 10, 12, and we can keep on going if we need to. However, if someone wants to ride on a bike, cycle, we can work at a 300 kilogram meters per minute, 600, 900, 1200, 1500, so on and so forth, and I can help you with the math as that's going. So that is really just dependent on what the individual wants to do in class. So we're going to need a person to take down their VO2 liters per minute every single minute, VCO2 liters per minute every single minute, VE or ventilation every single minute, and I'll show you on the computer. It will come up and you just have to write it down. VO2, milliliters per kilogram body weight per minute. This is the relative VO2. Respiratory exchange ratio. Carbohydrate, kcals per minute. Fat, kcals per minute. Heart rate, beats per minute. And then blood lactate. So blood lactate, I put these yellow boxes because we're only going to take blood lactate every 3 minutes, essentially at the end of every stage, because I don't want to poke the person in the fingers too much, but all of the rest of these boxes need to get filled out. These boxes right here, the carbohydrate and the fat, that will essentially be filled out after the fact because we're going to have to do some math with it. So hopefully that works for all of us in class. So let's work on just something in particular. Like one of the practice things I'm going to want you to do, let's take a look at this one. VE liters per minute and VO2 liters per minute. How that's going to end up looking is, say it's going to be 1.0, 1.2, 1.4, 2, 2.5, 2.7, something like that. And then VE, let's say that this is 100, 125, 150, 175, 185, why not, 200, something like that. Then you would just highlight both of those, insert, have a scatter plot like that, and as you can see, this should make relatively good sense to everybody in here. So VE liters per minute, then down here VO2 liters per minute. And I'm going to show you some graphs in class in order to determine where their ventilatory threshold is. There's going to be a point where ventilatory threshold goes up exponentially relative to their oxygen consumption. So hopefully we'll actually be able to see that pretty well. Now, I'm going to delete that. Now, let's say, for example, that we have like a respiratory exchange ratio of 0.7. What are some of the numbers that's going to give us? 0.7, 0.75, all that. Okay. Oop. 0.8. Okay. So here, if there is 1 liter of oxygen consumption and there is take home. I'll put this total one in there. Hopefully that'll make sense to us. All right, so say if there's 1 liter of oxygen consumption and we have an RER of 0.7. Now, we don't know these values yet. You're going to have to actually like go back and like get the data to know this. This is just going to be an example. So 0.7, right here, 0.7, that is 4.69. So is equal to that times 4.69. So that means that they're burning 4.69 calories per minute if they're consuming this amount of liters of oxygen. Now, if we go back to here, 0% carbohydrate, so essentially it's that times 0. That's somewhat obvious, huh? And then percent fat equals that times, well, it's just 1, really, 1 being 1%. Let's do this one so that maybe it makes a little bit more sense. 1.2, 0.75. If we go back here, 0.75 liters of oxygen per minute, 4.74. So equals that times 4.74. All right. So that means if the individual is consuming 1.2 liters of oxygen per minute, they are burning 5.688 kilocalories per minute. So now let's figure out how many carbohydrates, like how many, calories of carbohydrates that they're burning, and how many calories of fats that they're burning. So let's go back and look. That's not where I wanted to look. Sorry. So here, for carbohydrate, it's 17, and for fat, it's 83. Okay, so equals that times 0.17. So there equals that times 0.83. Is that math right? Yes, there we go. 83. I was a little bit unsure of myself. So this is essentially how we're going to derive the fat max throughout here. Here, let's do one more example together, because hopefully you're following along with this, that all of these we're just going to be taking down from the machine or the computer, whereas all of these actually have to be manually calculated. All right, let's say an individual is consuming 1.4 liters of oxygen per minute, which the machine will just tell us. And their respiratory exchange ratio is a 0.8, which the machine will just tell us. 0.8 right there. So let's figure this out. 0.8 RER, that is 4.8 calories per minute, equals that times 4.8, right? So 4.8, double checking it, 4.8, 0.8, there we go, 4.8. Now let's figure out how many carbohydrate calories per minute that this individual is burning. So here, fat, it's 67, carbohydrate, it's 33. So equals that number times 0.33 right there, and then equals that times 0.67. So all of that should work, meaning that we actually went down in the amount of fat calories that we're burning per minute, because we went up quite a bit in the carbohydrate calories that we're burning per minute. Hopefully all of that makes sense. In lab, I'll certainly help you make all of these. I'm very interested in the data that we get. So watch the other videos to understand what's going on overall, and like I will walk you through everything that we need to do in class. All right, see you soon.